Alright, recording. Okay, so yesterday we started lipids, and so we wrote all this about lipids are hydrophobic and how there's three categories. There's fats, phospholipids, and steroids. And so I think we started the fats. The fat is a glycerol and made out of fatty acids. And the glycerol is an alcohol. And why it's an alcohol is it has three hydroxyl groups, which is the OH groups. And then the fatty acids have the carboxyl group, the C with the double bond to the O and the OH, and then we have the hydrocarbon chain. And so that's what a fatty acid looks like. To hook them together, dehydration occurs, so we lose an OH and an H, and the molecule water comes off, and this O connects to this C. And so to get a full fat molecule is made from one glycerol and three fatty acids. So this is showing you one fatty acid. So then a second fatty acid would come and bond to this, and then another one would bond here. So we'd lose a total of 3 water molecules to make one fat molecule, because each fatty acid, as it attaches a water molecule, would be lost. All right? And so, so fats in general separate from water. Why? Because water molecules form hydrogen bonds with each other and exclude the fat. So the hydrocarbon chains, these hydrocarbons here, are nonpolar. So they don't have a charge. So water, when you put a fat molecule in to water, water is not attracted to the majority of the fat molecule. And so therefore it separates it out. Kind of like when we talked about oil and water. When you shake up oil, it'll temporarily mix up with the water, but then it separates back out. Why? Because the water molecules are attracted to each other, not at all to the oil. And so it separates out, and the same thing is going on here. So in a fat, the 3 fatty acids are joined to glycerol by what we call an ester linkage, creating a triacylglycerol, or you often hear it called triglyceride. So another word, when you see the word fat and triglyceride, they could be used interchangeably. So if we flip back to the category of fats, another way you could write triglyceride. So sometimes they'll say triglyceride instead of fat, so you need to know that those words can be used interchangeably. And so this is a fully constructed triglyceride. So this is your glycerol molecule. Here are your 3 fatty acids, and right here is the bond that joins each fatty acid to the glycerol. So we have 3 ester linkages, and therefore 3 water molecules came off of the molecule to make this fat molecule. So the fat molecule kind of looks like, to me, a little bit like the capital letter E, where the glycerol is like the backbone and the fatty acid chains are the prongs coming off of the letter E. I do want to point out, though, that fatty acids can differ from one another. So this picture here is showing you pretty much the fatty acids are all the same. They're the same length and so on. But one fatty acid can differ from another, though, in length. So this one could be 10 more carbons long, all right? And that would be a different fatty acid than this one, all right? And another thing that differs is whether or not there's double bonds in the fatty acid. And that means double bonds between the carbon atoms. So in this particular one, all 3 of them, there are no double bonds between the carbons. If there were, it would make them different fatty acids. So that's what can make one fat molecule different from another fat molecule, is what's true about the fatty acid chain. How long are they, where the double bonds are, or if there are any, and so on. So let's write that down. So fatty acids vary in length, number of carbon atoms, and then the number and locations of double bonds, so where those double bonds are. So, saturated fatty acids have the maximum number of hydrogen atoms possible and no double bonds. definition of a saturated fatty acid. Unsaturated is the opposite. All right, so unsaturated have one or more double bonds. And the major function of fats is energy storage. So fats have these long hydrocarbon chains. Hydrocarbons and those bonds have tons of energy in them. Fossil fuels are hydrocarbons. So they have a lot of energy. So fat has a lot of energy. That's why we don't need very much fat in our diet, because if you eat too much of it, then you don't need it and your body will store it in excess cells called adipose cells, and because you don't need that much energy. So it has tons of energy. So that's the main function of fats. So if we go back to this picture here, this one, this fat molecule is made from 3 fatty acids. Are these fatty acids saturated or unsaturated?
Saturated.
These are saturated. Saturated means that they have no double bonds. And let's talk about the word saturated. So if I said a sponge is saturated with water, what does that mean about the sponge?
It's filled.
It's soaked, it's filled.
So, well, the sponge has like a maximum, the water is taking up the maximum capacity.
That's right. So it can't absorb any more water. Absolutely. So why do we use the word saturated for these fatty acids? These fatty acids are saturated with what? They're saturated with hydrogen atoms. They're filled to the max with hydrogen atoms. Let's talk about why that is. Let me put this up here so I can write a few things. All right, so let's say this fatty acid down here, let's change it and make it unsaturated. So if I'm making it unsaturated, what am I going to do?
Make it
Add a double bond, right? So I'm just going to pick between two random carbons here. So here's your double bond. Now what's wrong with this picture?
You need to.
Take out 2 hydrogens.
Yeah, I have too many hydrogens now. Carbon can only make 4 bonds. I've got 5 going on here. So I have to get rid of 2 hydrogens, all right? So this is an unsaturated fatty acid. And so we would say that this fatty acid is not saturated or filled to the max number of hydrogens. Why? Because, and we can do this in the lab, if you have an unsaturated fat, what you can do is make it saturated by what we call hydrogenating it, adding hydrogen. So I could technically break this bond and add these hydrogen and make it saturated. So when there's a double bond, it's not saturated because you could add more hydrogens to it. All right, so that's what unsaturated means. And so, so if you have an unsaturated fatty acid and 2 saturated fatty acids, but notice that they all comprise one large fat molecule. So the fat molecule itself has 1 double bond in it. So because it has 1 unsaturated fatty acid due to this double bond, we would say the fat molecule, this is an unsaturated fat molecule because it has a double bond, all right? And the reason why it's an unsaturated fat molecule is because it has fatty acids that are unsaturated. So I only put 1 double bond. I could put more, so I could have this one be double bond, all right, this one. And then the more and more double bonds you have, you can classify it. We can say polyunsaturated, many double bonds. Mono means 1, monounsaturated, 1 double bond, and so on. But the fat molecule itself is classified as saturated and unsaturated, depending upon if the fatty acids are unsaturated or saturated. Okay? So, let's go back. All right, let's go back. So, fats made from saturated fatty acids are called saturated fats. That's what I just spoke about. So where do we find them? Mostly animal fats are saturated. Notice it says most, so there are some exceptions. Fish oil from fish, fish fats are not saturated, they're unsaturated, so that's an exception. All right, but most animal fats are saturated, so think about when you cook bacon. You cook it, when it's hot it's liquid, but if you let the bacon grease sit, in the pan and get to room temperature, what happens to it? It goes to a solid. So what happens is saturated fats are solid at room temperature. So with the exception of some, like the fish oil I gave an example of. And we'll talk about why they're solid at room temperature in just a second here. If you have too much saturated fat in your diet, it can be a bad thing. It can contribute to cardiovascular disease and form plaque deposits in the interior walls of your arteries and impede your blood flow to your heart, which is not a good thing. So limiting saturated fats in your diet is a good thing. And again, I'll talk about the construction, about why that is in just a second here. So that's saturated fat. So saturated fat, an example would be butter. That would be from an animal. And this is one example. This is an example of a saturated fatty acid. And so to make the saturated fat, you have your glycerol, and you have 3 fatty acids that are saturated. Okay. So then let's compare that to unsaturated fat. Fats made from unsaturated fatty acids are called unsaturated fats. Plant fats and fish fats are usually unsaturated. So the fish fat was what I was talking about, like it's coming from an animal, but it's not saturated, and therefore is not solid at room temperature. An exception for a plant fat is coconut oil. Coconut oil you can buy in the grocery store in a jar. It's solid at room temperature. All right, so that's an exception of that. All right, but plant fats are oils like vegetable oil, corn oil that you use for cooking and stuff like that would be an example of it, unsaturated. So unsaturated are liquid at room temperature. And we call them oils. And so they have double bonds in them. And so notice here, here's just a flask of some oil, so it could be a vegetable oil, and it's because that they have double bonds that makes the saturated fatty acids or unsaturated fatty acids because of the location of the double bond. Look at here, this is where the double bond between the carbon would be. So what happens is whenever there's a double bond, it causes a kink. You actually get a bend in the chain. So it actually changes the actual construction of it. And so let's look at why that is and how that plays a role in being solid versus liquid at room temperature. So if you have a saturated fat, so I'm just going to abbreviate here. If this is your glycerol molecule and here are your 3 fatty acids coming down, this is a saturated fat. Why? I can tell that without knowing anything because they're straight. So when you don't have double bonds, the hydrocarbon chains are going to be linear. When you have an unsaturated fat, you're going to have double bonds and you're going to have this kinking going on here in the chain. So that would be an example of an unsaturated fat. Now, saturated we said are solid at room temperature. Unsaturated fat we said are liquid at room temperature. Solid versus liquid, what's true about the molecules in terms of space in relationship to one another?
Solids are more close together.
Solids are more close together than liquids, right? So do you see with this linear fatty acid chains that saturated fats, if you had multiple, that they could pack closer together than the unsaturated that has these kinks? They take up more room, they can't pack as close together, and so therefore liquid at room temperature, solid at room temperature, okay? And so that's the reason why they have those states of matter at room temperature, okay? All right, and that is your fats. That's category number 1 of your lipids. So, category number 2 of your lipids is phospholipids. So we can, looking at the name of this, what functional group is on this? Phosphate group. So let's look at this construction. Two fatty acids in a phosphate group are attached to a glycerol. It's very similar to the triglyceride that we just looked at, except it has a phosphate group. The two fatty acid tails are what we call hydrophobic, but the phosphate group and its attachments form a hydrophilic head. We'll look at this head and tail region. So let's look at this picture here to help explain that. So the triglyceride had the glycerol with 3 fatty acids coming off of it. So the phospholipid has the glycerol, here's the glycerol, and 2 fatty acid chains. So these are your fatty acid chains coming off of here. Instead of a 3rd fatty acid chain, look at here, there's a phosphate group attached to it, all right? And then notice here also that there are some atoms up here. This says choline here. This group of atoms can change from phospholipid to phospholipid. So this changes, that's how one phospholipid can be different than the next, is what group of atoms is attached here. So this can be different, but what's the same between all phospholipids is the phosphate group, glycerol, 2 fatty acids. Another thing that can change between different types of phospholipids is not only this group, but your fatty acid chains. The length of them, the location and number of double bonds can change. And so therefore, if we had 2 different fatty acids, let's say this one also has a kink right here, then it would be a different phospholipid than this one. Okay, so that's how we can have different types of phospholipids. So let's look at this. So your phospholipid, the glycerol, and here's your fatty acid chain. This fatty acid is classified as what? What kind of fatty acid? Saturated. There's no double bonds here. And so they didn't draw any double bonds, and also it's linear, so it tells you it's saturated. This one is unsaturated. Notice at the kink, they put a double bond. Okay? So that's what we have going on there. And the phosphate group. Notice here, this part up here is called the hydrophilic head region. That's because these groups here are polar, they have charges, and so water is attracted to this part of the molecule. But the fatty acid hydrocarbon chains here are made out of just hydrogen and carbon, and therefore that's nonpolar, which makes these guys hydrophobic. Water is not attracted to these guys at all. So that's why they call this part the hydrophilic, this part hydrophobic, and they call this the head and the tail. From now on in your book, in a couple of chapters, we're going to look at these a little bit more in depth. You'll see phospholipids drawn like this. So the hydrophilic head and the hydrophilic tails, and so they're going to expect you to remember that the hydrophilic head, because it's polar, is polar groups and so on, and the hydrophobic tails are the hydrocarbon tails. All right, so phospholipids. Phospholipids are used in the construction of something in a cell. You guys know what it is? Construction of what in a cell? The cell membrane. So, do you guys remember how many layers of phospholipids the cell membrane is? 2. All right, 2. So let's talk about why that is. Can you see that if you put phospholipids into water, and our cells have water, a base solution inside and outside. If you put it into water, the head part, the water's going to be attracted to. The tail part, it's not going to be attracted to. So what happens is, and you can do this in the lab as well, if you take phospholipids and you dump them into water, how they'll arrange themselves is in a bilayer and form like a little ball, kind of like a little cell. So what they'll actually do is form, if this is the head and the tail, they'll go like this, where they form a bilayer, and this bilayer will go around and form a whole little sphere where the water will be on the inside and the outside. And the reason why they arrange themselves this way naturally is because the head parts have charges on them and the water are attracted to them. And so the head part orients itself towards the water. The tail part are just hydrocarbons. They don't have any, the water has no attraction to them, so they ended up in the interior part of the membrane. Kind of like yesterday when I was talking about proteins, and remember the three-dimensional shape of the proteins and the R groups interacting to stabilize that structure? Any R groups that are hydrophobic, where are they going to be? In the inside of the protein, so that the water-based, because they're not, the water-based solution on the outside is not attracted to them at all.
Have you seen those things where it's like you drop like a certain thing in the water and like it's like a bubble around the water? Is that, you know what I'm talking about?
Are you talking about magic sand?
No, it's not magic sand, but it's like when they're in the water you can't see them, but it's like a ball of water.
Oh, it's a,
Bubble tea stuff.
Yeah.
the what?
It's called like bubble tea. It's like
I think that's what
Is it like a toy?
No.
if you could put, okay, it's put your drink. It's like
No.
fad right now or
No.
something, and you can't see them in your drink.
Yeah.
But when you take them out, they look like little balls of water.
Because I did it with Mr. Pat.
Bubble tea.
I don't know that's exactly what he
They
means.
do it at restaurants too, like expensive restaurants.
I wonder if they're
I know what he's
phospholipids.
talking about though.
I don't know.
Oh, it's just in restaurants.
But I
I've
just
not heard
wondered
of this
if
bubble
that's-
tea. No, with it. That's interesting. Yeah, see if you can look it up, I'll look it up
You
too.
mix it up with like, you buy it from the science club, like, you
Okay.
mix it up with two things. No, it's a food web thing, 'cause it's like we actually make it at restaurants.
Can you ingest it? Can you actually?
Yeah.
We actually eat them,
Okay,
yeah.
interesting. I've not seen this. I don't know, so it might work something exactly the same, it might be a phospholipid thing, right? Yeah. Oh, that would be fun to do. Alrighty, so those are your phospholipids, and so let's write a little bit more. Phospholipids are added to water, they self-assemble into a bilayer, which is what I was just talking about, with the hydrophobic tails pointing towards the interior. And that's because the hydrophilic heads are attracted to the water. So then we get this bilayer arrangement that we find in cell membranes. And so basically the function of phospholipids is to comprise the major component of all of our cell membranes. So that's their function. What was the function of triglycerides? Fats that we just learned that?
Energy.
Energy, right? They have lots of energy. And those are your phospholipids. So then we only have one more class of lipids, and that is your steroids. And this is a picture of the phospholipid bilayer. It gives you, it's a better picture than mine. It gives you more of a three-dimensional, kind of showing the sphere, right, that it forms with the tails in the interior. All right, so steroids are your last class of lipids. Steroids have a totally different construction than the other two. They're characterized by their carbon skeleton consisting of 4 fused rings. There were no rings in the triglycerides and the phospholipids. And cholesterol we'll look at several points in the course. It's an important steroid. It's a component in animal cell membranes. So some cholesterol is good, and it's actually a component of the cell membranes. We'll look at that a little bit later. And then some cholesterol is bad. So although cholesterol is essential in animals, too much of it, high cholesterol amounts, can also lead to cardiovascular disease. Like, what was the other molecule we just talked about that could lead to cardiovascular disease? Saturated fats, all right, can lead to cardiovascular disease as well. So here's the construction of your cholesterol. This is a picture of cholesterol. So when it says 4 fused rings, fused means that they share a side. So here's 1, 2, 3, 4, but you see how they share one side here, one side here, one side here. That's what fused means, all right, is to share a side. There are lots of different types of steroids. Cholesterol is just one type. What makes one steroid different than the next? the location, number and location of double bonds. So here is some double bonds here. What chemical groups are attached to it coming off of it and where those chemical groups are. And then most steroids also have a hydrocarbon chain coming off of it. And so how long that hydrocarbon chain is, if there's any double bonds, where it comes off the molecule, can all make one steroid molecule different than the next. So in your packet that I finished checking off yesterday, there was an actual picture of cholesterol. So what I'd like to do is refer back to that lipid part of your packet, where you pasted all the pictures. Get that out and let's go through cholesterol since we're talking about it. Make sure that you understand what they asked you to do. Alright, so we finished the proteins up yesterday, so group 2, the steroids, and they had a picture that's exactly, looks almost identical to the picture I just had up in your notes. And so in the reading here, it told you that there is a carbon atom not drawn in most cases at every point in each of the 4 rings and in the side chain. So what that's telling you is that to make it simpler to understand, they didn't draw in all the carbons and hydrogens. I went ahead and drew them in here so you can see how busy it is. So you can see that at each point in each ring is a carbon atom, and even at each point in the linear part here, coming off of the side chain, is a carbon atom. And then each carbon can make 4 bonds, right? And so unless they drew another atom in there, like right here off of this carbon is an OH, you are to assume that whatever bonds that they didn't show are the carbon atom is bonded to hydrogen. So when it asked you to redraw it here, so I didn't redraw it, so you would start like, let's say with this ring here. So you'd go here and you'd draw your 6-sided ring like this with your carbon here. All right, so that would be this ring, and then we could do the next ring like this. All right, and that's your next ring. Notice that there's a double bond here. So double bond here, and you can continue to draw the carbon atoms that way. And then what you do, and do the other 2 rings and so on. But I just want to model for you how to think about the number of hydrogen atoms that go on there, because I had a lot of people ask me questions about it. So like when we look at this carbon here, it's making 2 bonds to each of the adjacent carbon. So that means carbon makes 4 bonds, so that means that this carbon must be making 2 more bonds to 2 hydrogen atoms because of that. So basically what you do is you go to each carbon and look to see how many bonds they're currently making, and then add as many hydrogen as it takes to give it a total of 4 bonds. So along the side here, that would also be a hydrogen, 2 hydrogens here. This one has 2 bonds, so 2 hydrogens here. All right, same thing with this one. Notice this carbon right here. It already has 1, 2, 3, 4. So you don't add any hydrogens to that one. It's already making 4 bonds, all right, to that. So no hydrogen coming off of this one. This one then has 1, 2, 3, so you'd only need 1 hydrogen coming off of it. And so on and so forth. And so that's how you do that to understand that. And so in our textbook, often they'll just leave out all the carbons and hydrogens, and they're expecting you to realize that there are carbons there at each point, and that anything up to 4 bonds means that there's that many hydrogens attached to it. So the questions on the other side ask you to locate the double bond. So this is the double bond right here. All right, so that's your double bond. And whenever there's a double bond, that means 1 less hydrogen can be attached. So then let's look over here. So we put an arrow to the double bond, redraw the cholesterol molecule, add the hydrogens, I just talked about that. And then I asked you to paste your steroids. So you should have 3 things pasted here, so that each one of these have the 4 fused rings. So adding the hydrogen on, remember again, at each point is a carbon atom. So like for instance, this one right here has 1, 2, 3 bonds, so I only added 1 hydrogen. Same thing with this, 1, 2, 3 bonds, only 1 hydrogen. This one here is already making 4, 1, 2, 3, 4, so I didn't add any hydrogens to that carbon atom at that particular point. All right, same thing with this carbon atom. This one was making 3, so I added 1. And so that's kind of what you do, is to add the hydrogen onto it. These are 3 different steroids. What makes them different? They're 4 fused rings, but what makes them different is, look at here, this one has 3 double bonds in this ring, this one only has 1. This one only has 1. And so the number and locations of double bonds is what makes them different steroids, as well as the functional groups coming off it, the groups. So OH here versus a double bond of the oxygen. We have a different group of atoms here than we have in either one of these, and so on. So that is what makes them different from one another. Okay? All right. There's another group with the fats. This is looking at the fatty acids. So let's look at that. I want to point out just one thing with the representations in the box, just to make sure that you understand those. So letter C is kind of like how our pictures in our notes just described a fatty acid. So the fatty acid here has the carboxyl group right here, and they have your long chain of carbons, and then the very end carbon is always going to have 3 hydrogen, because if you're ending the carbon chain, you don't have another carbon, and so it has that 3 hydrogen at the end, all right, for that. So looking at this, is this saturated or unsaturated? This one's saturated, there's no double bonds here. So I just want to point out then A and B. Notice here A, let's look at why it's the same. So the end is CH3, that's this one right here. And then notice all the carbons between the CH3 and the carboxyl group have a C and 2 H's coming off of it. So that's CH2, 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 and so on and so forth until we get to the carboxyl group at the end. And so this right here is shorthanding that and saying, okay, CH3 is at the end, and then we have a group CH2, we have 10 of those. And so if we count those, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, there are 10 of those there. That's why they put the 10 and then connected to the carboxyl group. So all 3 of these are depicting the same molecule. And I just want you to be aware of that. So if you see that, you can recognize that, oh, this is the carboxyl group and its long chain of carbons and hydrogens, and must be a fatty acid. All right, so let's go to the questions here. They asked you how many fatty acids do you have in your collection. Your answer should be 3. All right, and if we turn it over, these are the 3 that you should have in your collection. So these are the 3 here. It's the carboxyl group, and then the long chain of hydrocarbons. And so those are your fatty acids. And then it asks you how many are saturated. You should have 2. And how many are monounsaturated? Mono means it has just 1 double bond, and you should have 1. So this one right here in the center has a double bond. The rest of them are all single bonds, which makes them saturated. The next one, if a monounsaturated fatty acid has 1 double bond in its hydrocarbon chain, how do you think you would define a polyunsaturated fatty acid? That means it has multiple double bonds, right? So I'm going to ask you to draw a short polyunsaturated fatty acid below. So what you have to have, yours doesn't have to look exactly like mine, but you should have a carboxyl group on one end, and your carboxyl group doesn't have to be on the right-hand side. You could have started out with a carboxyl group over here, and then you have your carbon chain, and so you have to have, I put 3 double bonds here. Yours doesn't have to be exactly where mine are, or the same length of the carbon, but I put 3 double bonds, but make sure where you put the double bonds, that your carbon is only making 4 bonds, all right? So those carbons can only be bonded to one other hydrogen. And then at the end, you have that CH3, all right? And so that's that. And so then you have this on the other page, okay? right on to look at carbohydrates. So carbohydrates, we're gonna go back to 5.2, which is on the back of the first page of your notes. Alright, so carbohydrates include sugars and the polymers of sugars. Remember, polymer means a long chain. The simplest carbohydrates are monosaccharides or single sugars. And carbohydrate macromolecules, big carbohydrates, are called polysaccharides, and they're long chains of single sugar molecules. So with carbohydrates, we're going to classify carbohydrates based upon their size. So one single sugar is called a monosaccharide. Mono means one, saccharide means sugar, so one sugar. And in living organisms, sugars are in the form of a ring. And so we'll talk a lot about glucose in this class. So glucose is in a ring. One ring of glucose is a monosaccharide. Then we can hook two glucoses together. And that is not a monosaccharide, it's a disaccharide. Di means two, you have two sugar molecules together. And then we kind of jump into size from two to many sugars hooked together, and that's a polysaccharide, poly meaning many. So how we're gonna tackle carbohydrates is by the size. We'll start out with the monosaccharides, then talk about disaccharides, and end up with polysaccharides. So that's kind of how this is organized. So let's look at the monosaccharides. Sugars, you might want to put parentheses here behind sugar, monosaccharides. That's what we're talking about. That's the basic sugar of a carbohydrate. It's the monomer of a carbohydrate. Monosaccharides have molecular formulas that are usually multiples of CH2O. And I'll give you an example here in just a second. Glucose is the most common monosaccharide that we'll talk about. And monosaccharides are classified by the location of their carbonyl group and by number of carbons in the carbon skeleton. So where the carbonyl group is and how many carbons long they are. So let's talk about glucose for a second. Raise your hand if you remember from biology the formula for glucose. Some of you guys put them in the back recesses of your mind.
C6H12O6.
Absolutely. So glucose is C6H12O6. Now does it ring a bell?
Mm-hmm.
Yeah. All right. So notice that this follows the same formula here. What this really means, CH2O, is that in monosaccharides there's double the H's as there are C's and O's. So that's what that means. So 12 is double 6. All right, of that. So that follows that same kind of formula. So glucose is the most common monosaccharide. And then it says they're classified by the location of their carbonyl group. Now, raise your hand if you can tell me how to draw the carbonyl group. You remember its construction. What do I have to do to draw the carbonyl group?
Other than just a C with a double bond with O.
Absolutely. So C with a double bond to an O. That's called the carbonyl group. So then let me ask you this. So molecules, the carbonyl group can be located in different parts of the molecule. So if I have two molecules that are 3 carbons long, let's say the carbonyl group here is at the end, and here it's coming off the center. All right, this is what these guys are called, different molecules as a result of that. If the carbonyl group is at the end, it's called something that starts with an A. An aldehyde, that's right. And if it's in the middle, it starts with a K. Ketone. And so this is going to become important in just a second when we look at the next picture. All right, so So here's the carbonyl group and here's the carbonyl group. It's just the location of that varies. And this is what's going to help make one sugar molecule different from the next. So let's look at the next picture here. Okay, let's look at, first of all, the columns. So tri, pent, and hex. And then after that is the ose. Anytime you see ose at the end of something, it's referring to a sugar. So when you look at the name of something and it ends in OSE, it's a sugar molecule. Tri, pent, and hex. What do you think that's referring to? The number of carbons. So notice this column here. There's three carbons here, 3 carbons here. This column here, each one of these have 5, and this column here has 6. So they can be classified and looked at in terms of the size or the length of their carbon chains. The second thing that we focus on in looking at differences between sugars is the rows here. Notice this says aldoses and ketoses. Ose means that the sugars. Ald is referring to aldehyde. So notice here, and the ones in the top row, all the carbonyl groups are along the end of the molecule. If we look at here, the ketoses, that's referring to ketones, all of the carbonyl groups are somewhere in the middle of the molecule, not at the end. And so that's how they classify that. Now, every carbon atom, besides the one that's double bonded to the oxygen, no matter where you look, every carbon atom is also bonded to a what group? Besides the carbon that's double bonded to the oxygen, every other carbon atom in your sugar molecule is bonded to what? A hydroxyl group, OH. Okay, and so everyone has that. So that's a classification of sugar. All right, they have the carbonyl group, and every other carbon has an OH, and they're just made out of carbon, hydrogen, and oxygen. Now, all of these are linear in shape, and like I said, we'll talk a lot about glucose. But what happens is in water, these linear sugar molecules will fold and form a ring. So from now on, when we look at, let's say, glucose, we'll see it in a ring form, because in living things are in water-based solutions, and so the sugar molecule will form rings, and so that's how we'll see it from now on. All right? So what's the purpose of monosaccharides like glucose? It's for fuel or for energy for our cells, and then it can also be used as raw material for building molecules. And as I just said, they're often drawn as linear, like we just looked at. In aqueous, that's water-based solutions, they form rings. And so that's what this picture here is showing you. Here's the linear form, and it's showing you bending around here. And so we'll see it written in rings. So let me explain a little bit about this. So here's your carbon atoms joined in, that are drawn in, I should say, and here's the abbreviated structure. Oftentimes you'll see it written like this, and so from now on you already know that each point is a carbon atom. And then the numbers here associated, they number the carbon atoms 1 through 6, like for the C6 in the sugar molecule. All right, so that's what those numbers mean. All right, so we'll look at it from now on in the ring. All right, so those are your monosaccharides. So disaccharides are formed when a dehydration reaction joins two monosaccharides. And this has a special name, the bond between them. It's called a glycosidic linkage. So this picture here shows you the making of two different disaccharides. So the first row is making the disaccharide maltose. Maltose is made from the 2 molecules of glucose. So here's our abbreviated ring structure. So an OH comes off of one, an H comes off of another. We lose a water molecule here. Now look at this O is no longer bonded to anything, and neither is this carbon. So what happens is this carbon bonds to this O. That's why it has like an O sitting here, all right, in the middle. That O is this O right here, okay? And that's your disaccharide. Now look at here how they named it. It says a 1,4 glycosidic linkage. Glycosidic linkage is just the bond between the two monosaccharides. And the 1 and the 4 comes from, it's between the carbon atom number 1 of this molecule and carbon atom number 4 of this molecule. So that's why they call it 1,4, all right? So then we look at sucrose. Sucrose is just our table sugar that we eat probably too much of. And that is made from the monosaccharides glucose and fructose. So again, taking off an H and an OH. Notice fructose has a little bit different shape, the ring, but it still has 6 carbon atoms. It has 1 here that's not part of the ring, 2, 3, 4, 5, and then the 6th one is not part of the ring. So this is fructose, loses a water molecule. This O is now connected to this carbon, and that we have that, all right? And so the first number 1 carbon and 1, 2 carbon, and so therefore it's a 1,2 glycosidic linkage. All right, so looking at this, let me ask you this, okay? I already told you, or Shane told us that glucose had a formula, or Sage, of C6, H12O6. What's the formula for fructose? Look at it and tell me what the formula for fructose is. What'd you say, C?
C5H10O5.
What do you think? So fructose is this whole molecule here. Let's look at the C's. 1, 2, 3, 4, 5, 6. See how there's 6 C's there? All right. So let's change that to 6. So then we're going to change these 2 as well. So how many H's?
12.
There should be 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. All right, so 12. And how many O's?
6.
6, yeah, 1 right here, 2, 3, 4, 5, 6. Look at, they're the exact same. They're just put together differently here. So they're the exact same molecular formula. So then, what we do is we add these 2 together to get your formula for sucrose. So what I'd like you to do is looking at this, if you knew that you're adding these together, what I want you to do without actually counting, don't count the number of sucrose, or the number of atoms in sucrose, don't sit there and count them. What I'd like you to do is to write the formula for sucrose. Knowing that glucose and fructose have the formula C6H12O6. Very common answer is this. C12H24O12. Very common answer, but a wrong answer. All right? So why is it not this? Maria?
We lose the water molecule, so we have to take out 2 hydrogens and 1 oxygen.
That's right. In order to hook these together, you really don't have 2 hydrogen and oxygen because it comes off as water. So therefore, instead of C12H24O12, you should have, the carbons aren't affected by water leaving the molecule, but the H's are. So we should have 22 and what?
11.
11. All right, absolutely. All right. How many people got that? All right, very good. All right, nice job. Alrighty. I'll stop here. I'll stop here. I'll talk about polysaccharides.
I'm not worried.
Me too. I'll actually get some